So in this lecture, we introduced the negative binomial distribution. It's going to turn out that the negative binomial distribution is among the most popular distributions for modeling RNA-seq or any data set which involves sequence counts. And it's popular in part because, unlike the normal distribution, it is a count distribution. So it seems natural to model sequencing data with it, since sequencing data are also counts. But unlike the Poisson distribution, it doesn't have an assumption that the mean equals the variance. Now, we're going to argue, in fact, that that the negative binomial distribution is still a highly parametric assumption. It still argues that there's this kind of strict relationship between the mean and the variance, even if the mean does not exactly equals the variance. And it's often going to be true that a t-test will actually give as good or better results, even though the t-test is not is continuous and isn't a count distribution. But nonetheless, the negative binomial distribution is extremely popular. DSeq and EdgeR and many other algorithms use the negative binomial distribution for their inference. And as a bioinformatics analyst, you're certainly going to encounter it, and you need to understand it. Somewhat paradoxically, although we don't think of sequencing experiments as being tournaments, the negative binomial distribution in some ways is the easiest to understand if you think about it in terms of a tournament. So with the negative binomial distribution, there's two free parameters. P is the probability of a loss. So think of you're in the tournament, and P is the probability that you lose a game, and R is the number of losses before you're removed from the tournament. What the negative binomial distribution predicts or gives you the probability density function for is K, where K is the number of wins. Notice that K can go from 0 to infinity here. So unlike the binomial distribution, where if you flip the coin 25 times, you can only see 25 heads, the way the negative binomial distribution is set up, you might have a probability of a loss of 0.3. There's some probability that you would have 100,000 wins. Now, that's not a very high probability, but it's not exactly zero, as opposed to the binomial distribution, where if you flip the coin 25 times, there's zero probability of seeing 26 heads. Okay, so the probability density function is actually pretty easy to describe, right? So the probability of each individual sequence of wins and losses is p to the r times 1 minus p to the k, right? So you're going to stop after 3 losses, right? So you know that there's going to be exactly 3 losses. You're going to have 0 wins or 1 wins or 2 wins or 3 wins or 4 wins to go with your 3 losses, and the probability of all of those is simply 1 minus p to the k. Since the last game is a loss, there are k plus r minus 1 choose r minus 1 ways of organizing the flips. Right, so that you lose a degree of freedom with the negative binomial distribution. I know that the very last game is a loss, so I have k plus r minus 1 games, besides not including the last one, and I can organize them in r minus 1 ways. And another way to think about that is that if you distribute the wins and losses, if you're allowed 3 losses before you lose the tournament, you're distributing your wins and losses. There's only 2 losses that you're distributing among your win plus loss minus 1. Your number of wins plus 2 ways of having the you have k plus r minus 1 ways of having the flips, and you only have the 2 losses that you can organize. The last loss you can't organize. It's not free to move around because it's you know that you're losing on a loss. So there's this number of ways of organizing the wins and losses, and the probability of all those wins and losses is this. So you just multiply those 2 together, and you get the probability density function. Just to demonstrate that this is in fact correct, we can simulate this in R. So here I simulate 10,000 tournaments. The probability of losing a game is 0.4. The number of losses before I'm removed from the tournament is 3. The distribution of wins goes from 0 to 40. Right. Now in this case, I'm actually only plotting this out from 0 to 40 because there's no point in plotting it out really beyond 25. But again, as a true probability density function, actually this goes to infinity. But again, it gets very, very close to 0 after 22, 23 wins. So there's no point in plotting it out or calculating it after 23 or 24 wins. The number of trials is 10,000. So I'm just going to hold as my result vector the number of wins that I had. And then I'm just going to go through and grind through the simulating the actual tournament. So it's number of wins, number of losses, until I get to 3 losses, play the game. I have a 40% chance of losing, 60% chance of winning. Keep going until I get my 3 losses, and then just record the number of wins that I had. So the argument that I made was that the probability density function of this thing is this times this. So that is choose k plus r minus 1, r minus 1, right? That's this here. And then the probability of organizing the wins and losses is this, or the probability of seeing each individual string of wins and losses is this. So that's just that. So that's my negative binomial distribution. And so I have my histogram of wins, right? So the this is the probability that I'm going to see 5 wins and 4 wins and 3 wins and 2 wins and 1 win and 0 win. The simulated results are shown as the bars of the histogram. The probability density function that I get by multiplying these two values together is shown here, or equivalently, of course, I can save myself all of this typing and just use R's built-in function dn binom to get the same line, the same fit. Okay, so dn binom is built into R, as the last line of the code in the last slide showed. Right? And so if dn binom is built into R, we already know these 4 functions that are in R with our usual prefixes that have been present for all of the distributions that we've looked at so far this semester. So there's dn binom, pn binom, qn binom, and rn binom, which of course is the probability density function, the cumulative probability density function, the inverse cumulative probability density function, and random sampling from the negative binomial distribution. So we already know how to use all of these because these suffixes, or these prefixes, are the same as they are for all the other distributions that are in R. So we're going to state without proof the mean and the variance of the negative binomial distribution. So this will be a smart people tell us. So it's going to turn out that the mean of the negative binomial distribution is 1 minus p times r divided by p, and the variance is 1 minus p times r over p squared. So if you have a 40% chance of loss and r equals 3, you can expect to win 4.5 games. And of course, this is going to impact the expected value of a tournament, which of course is one of the homework assignments that you have outstanding at this point. The variance is going to turn out to be 1 minus p times r over p squared. So and notice the variance is actually quite high, and this is going to be the main feature of the negative binomial distribution, is that the variance is always higher than the mean. So if you can win 60% of your games, and you're kicked out of the tournament after 3 losses, the mean is going to be 4.5, but the variance of the number of wins that you can expect is actually quite high at 11.25. So for a player who wins 60% of the games, the mean plus or minus standard deviation is 4.5 plus or minus 3.4. Right? So there's a lot of variance, a higher amount of variance in the negative binomial distribution than in a straight Poisson distribution, which is to say that the variance is always higher than the mean. And again, if we look at our simulated tournaments from the previous slide, we can show that although we're not going to prove these formulas for the mean and the variance, that they're pretty close to what we get when we just run a large number of simulated tournaments. We get a mean of 4.5 and a standard deviation of 11.23, which is within round off error, or within expectations, I would say, or is pretty close to the 4.5 and 11.25 we were expecting to see. And of course, as you guys know by now, by the law of large numbers, if we'd run an infinite number of tournaments, then we would approach these values exactly. Now, again, you might be asking, well, what does sequence experiments have to do with tournaments, right? Why is the negative binomial distribution used so often? For sequencing experiments, it's weird to think about a sequencing experiment as being the results of a tournament. But the great trick of the negative binomial distribution, the thing that really makes it incredibly useful, so for a RNA-seq experiment, right, for a particular gene, you might not know R and P, but you would know the mean and the variance, right? So you could say, oh, this is actin, it's expressed 2.3% of the time, and across all of the samples, the variance was 1.7% or whatever, right? I saw the mean was 12,000 counts, and the variance across all the sample was 300 counts, right? So I know the mean and the variance for the results of my genomics experiments, right? And so if you take these equations and just rearrange them, right, if you know the mean and the variance, so here's the mean and the variance, you can then solve for PNR. Right? So you can take a DNA, the results of an RNA-seq experiment or any sequencing experiment. If you know the mean and the variance, you can then cast them as the probability of a loss and the number of games that you're going to get allowed to play before you're tossed out of a tournament. Right? And then you can use this P and R for background inference for a different set of conditions. And so if I have a set of samples in one condition and I have the mean and the variance for those samples, I can use P and R to calculate the negative binomial distribution, and then I can use that expectation of the negative binomial distribution for another set of conditions. And that's, to simplify a little bit, that's more or less the way algorithms like DSeq and edgeR work. And again, I think we've seen this figure a bunch of times. You want to be using the negative binomial distribution rather than the Poisson distribution, because if you take essentially any RNA-seq experiment and each one of these dots represents an individual gene, and you plot out the mean versus the variance, it's basically just never true that the mean equals the variance. So if you did inference with the Poisson assumption, you would get wildly inaccurate p-values for all of these genes here, because the true variance is up here, but under the Poisson distribution, you'd be estimating the variance there. If you estimate the variance for an inference test 2 or 3 orders of magnitude below the actual variance, the p-value is going to be pathologically small. Right? So this is a fit to a real data set, to a real RNA-seq data set under the assumptions of the Poisson distribution, and then under the assumptions of a negative binomial distribution, where we can increase the variance by essentially decreasing the tournament length. Right? So again, if we take these values for R and P and we arrange them, we can actually show, right? So now solving these two equations now for the variance, for the observed variance, what you can show is that the observed variance equals the mean plus 1 over R mean squared. Right? So if the tournament is infinitely long, that's like a Poisson distribution. If you're never kicked out of the tournament, it's just like flipping a coin over and over again. And in that case, the mean equals the variance. But as the tournament gets shorter, as the number of wins, of the number of losses that you can have before you're kicked out of the tournament gets shorter, then the mean, then the observed variance it becomes larger than the mean by this factor of 1 over R mean squared. Right? So this kind of flexibility in the Poisson distribution for algorithms like DSeq allows the inference to be done against this orange line from the negative binomial distribution rather than this purple line for the Poisson distribution, and clearly that kind of inference is more appropriate for RNA-seq data. Again, I'm going to argue a little bit later that actually none of this works as well as the simple t-test, but you can see that if you had to choose between a negative binomial distribution and the Poisson distribution, that the negative binomial distribution is a much better choice than the simple Poisson distribution. And the last thing that we'll do here for this in this mini lecture is to demonstrate that the negative binomial distribution, in fact, does have higher variance than the binomial distribution. So here I just have I'm going to vary R from 10 to 50 to 100 to 200. Right, so this is the number of losses before you're kicked out of the tournament, and I'm going to compare a plot of the negative binomial distribution, dn binom in red, and just the binomial distribution in black, right? And so when we compare similar parameters between the negative binomial distribution and the binomial distribution, what we can see is that when R is small, right, the variance, the width of this curve of the negative binomial distribution is larger than the variance of the binomial distribution, right? And again, right, when R is small, the negative binomial distribution has a variance that's higher than you would see under Poisson assumptions. But when R gets to be big, when the tournament gets to be infinitely long, then the variance of the negative binomial distribution approaches the variance of the binomial distribution or the Poisson distribution if P is small. Okay, so these are just graphs that demonstrate that this algebra is correct. That if the tournament length is small, you get a boost to the variance. If the tournament is really long, then the mean equals the variance, which is the Poisson assumption, or the assumption under the binomial distribution when P is small, because n times P times 1 minus P equals n times P when P is small.